All right, the intermediate value theorem says, well, first of all, the book says, is an important theorem concerning the behavior of functions that are continuous on a closed interval. Now, when we have theorems in any math, but especially now that we're in calculus, you got to pay attention to the hypothesis, or it's usually more than one condition, hypotheses of the theorems, the conditions that must be met for the theorem to be true, for the conclusion of the theorem to be true. All right? So on this theorem, it says if f is continuous, all right, we've talked about continuity at a point. We've talked about continuity on open interval. We talked about continuity on the closed interval from A to B. All right, so f must be a continuous function on the closed interval from A to B. If it's not continuous on that entire closed interval, then this theorem does not apply to this function. Also, k is any number between f of A and f of B. Now, f of A is the y value of the function at the left-hand endpoint of the graph, isn't it? F of B is the y value of the function at the right-hand endpoint of the graph. Following me? K is a number that's between them. So, for instance, if f of A was 5 and f of B was 10, then k is some number between 5 and 10. All right? So, those are the conditions that have to be met. You have to have a function that's continuous on the entire closed interval. You have to have a number that's between the y values that occur at the endpoints of the graph on this interval. When those two things happen, then there's at least one number c in the interval from A to B. So c is an x-coordinate. There's at least one x-coordinate between x equals A and x equals B, including x equals A and x equals B, such that the value of the function at that x-coordinate equals that number we chose between f of A and f of B. Now, this all sounds complicated, right? It's not. It's really not. Let's say that's our x-axis. There's A, there's B. Here's our y-axis. So that would be f of A, that would be f of B. K is some number in here between them. Think about it. If the function that I have not graphed yet is continuous from one end all the way to the other, doesn't the y-coordinate of k have to be on that graph at least once? It has to be. It could be more than once, right? But it has to be at least once. If f is not continuous, then it doesn't have to be, does it? But if it's continuous, it does. And I kind of like their little example here. It's fairly simple. All right, so suppose that a girl is 5 feet tall on her 13th birthday and 5 feet 7 inches tall on her 14th birthday. Wow, she had a hard time staying in clothes. Then for any height h between 5 feet and 5 feet 7 inches, there must have been a time t when her height was exactly h. Right? You don't just skip instantaneously. She came close. That's about as close as you can get. But you can't just skip from 5 feet to 5 feet 7. You cannot skip any of the heights in between. It's impossible because growth is a continuous function. Okay? Make sense? All right. Now, the intermediate value theorem guarantees the existence of at least one number c in the closed interval. The theorem doesn't tell you how to find it. It just guarantees that it exists. Okay? There may, of course, be more than one number, c, such that f of c equals k, as shown in figure 1.35, that one. A function that is not continuous does not necessarily exhibit the intermediate value property. For example, the graph of the function in figure 1.36 jumps over the horizontal line given by y equals k. So for this function, there is no value of c in the interval such that f of c equals k. So it's got to be a continuous function, okay? And look, and k's got to be between f of a and f of b. If k was up here, is there any guarantee that there's going to be a place on the graph that has that y coordinate? No, not at all. All right? Now, I want to point out to you this. If f of a and f of b have opposite signs, in other words, one of them's positive, one of them's negative, then the intermediate value theorem guarantees at least one zero or root or place where the function value equals 0, where the y coordinate equals 0 on that closed interval. All right? So, back to this. If that's f of a, if that's the point A, f of a, and over here is the point B, f of b, doesn't there have to be at least one place between those 2 points where the graph crosses the x-axis? Intermediate value theorem guarantees it, doesn't it? Okay? Because the intermediate value theorem guarantees there's at least one place where the y coordinate equals 0, since f of a is negative and f of b is positive. You with me? Because this is kind of big. So that means, and there's all these different names, that means there's at least one 0, at least one root, at least one place the graph crosses the x-axis, at least one place where the y coordinate equals 0. Questions? 77. All right, let's see here. Let's take a look at number 58. All right, number 58 is on page 80. The directions say to find the constant a or the constants a and b such that the function is continuous on the entire real line. So 58 is a piecewise defined function. One piece involves trigonometry, so g of x equals 4 times the sine of x over x when x is less than 0. And then the other piece is linear. G of x equals a minus 2x when x is greater than or equal to 0. Now the direction said find a or find a and b. This one just has a. So we're supposed to find a to make this function continuous at x equals a. Or, excuse me, at x equals 0. Now, why is 0 the only place I'm concerned with? It's where they meet or don't, right? The top definition, 4 times the sine of x over x, since x cannot equal 0, look at the domain of that. X cannot equal 0, so that function is going to be continuous on its entire domain. And then that's linear, so that's going to be continuous on its domain. So the question is, do they connect? Well, actually, the question is not do they connect. The question is, make them connect. We have to find the correct value of a that will make them connect. Okay? Now, for g to be continuous at x equals 0, what has to happen? Go back to your definition of continuous at a point. There are 3 conditions. Okay? Since 0 is our c, f of 0 has to exist. The limit of the function as x approaches 0 has to exist. And the value equals the limit. Those 3 things have to happen. That's our definition. So, this has to happen, doesn't it? For the limit to exist, and I think I've summarized this quite nicely. Hang on. For the limit to exist, the limit as x approaches 0 from the left has to equal the limit as x approaches 0 from the right, doesn't it? Now we're getting the definition of limit. The limit from the left has to equal the limit from the right, and when they do equal, that's the limit. Okay? So that guarantees the limit of g of x as x approaches 0 exists. G of 0's got to exist, and g of 0's got to equal the limit of g of x as x approaches 0. So that has to equal that, has to equal that. Alex? Okay. You're confused or unconfused? All right. What's wrong?
Why didn't you give us as x approaches something or whatever under g of x?
They didn't give us that. I figured that out. Why don't they? All right, because that's the only place we might have a discontinuity, correct? The directions say to find a such that the function is continuous on the entire real line. So we've got to make it so that the two parts of the function connect. How do we know they connect? Well, because they got to be continuous. What's the definition of continuous? 3 conditions. F of c exists. So for us, g. So for us, g of 0 must exist. The limit of the function as x approaches c must exist. So for us, the limit of g of x as x approaches 0 must exist. And the value of the function must equal the limit of the function. So for us, g of 0 must equal the limit of g of x as x approaches 0. So I could have written a step in that said the limit of g of x as x approaches 0 equals g of 0. That has to be true. And if it is true, that takes care of all 3 conditions, doesn't it? Both things have to exist if they equal each other, and they equal each other, which is the 3rd condition. So all I did is say, okay, since this is a piecewise function, that only exists when the limit of g of x as x approaches 0 from the left equals the limit of g of x when x approaches 0 from the right. So I replaced that with that. Does that help? Okay, everybody see the reasoning? Is it going to be important for you to know the 3 conditions that have to exist for a function to be continuous at a point? It's kind of vital, isn't it? Can something be kind of vital? Like a spleen? All right. So, let's make it true for this problem. The limit of g of x as x approaches 0 from the left. From the left is this function, isn't it? Because the domain x is less than 0, those are the numbers that are to the left of 0. So to find the limit of g of x from the left of 0, I've got to use 4 times the sine of x over x. All right, to find the limit of g of x as x approaches 0 from the right, I've got to use the definition of the function whose domain has the x's that are to the right of 0. So that would be the limit of a minus 2x as x approaches 0 from the right equals g of 0. Now, g of 0, which definition do I have to use? The bottom one, because it's got the greater than or equal to. So g of 0 is a minus 2 times 0, right? A minus 2x, replace the x. Everybody with me to the little blue check mark? So far? All right. Now, what's the limit as x approaches 0 from the left of 4 times the sine of x over x? It's 4. Okay? Now, I don't know how many steps it's going to take you to do that. It took me 1. Because we've got a theorem when we listed properties of limits. One of the theorems, one of the properties is when you have a constant, you can factor it out and set it in front. So I can turn that into 4 times the limit as x approaches 0 from the left of the sine of x over x. And what does our theorem say? The limit of sine of x over x as x approaches 0 equals 1. So I can turn that into 4 times 1 pretty quickly. Okay? Now, the limit of a minus 2x as x approaches 0 from the right, since that's linear, can't I substitute 0 in for x? Yes. So when I do substitute 0 in for x, don't I get this that we said g of 0 equals? So I've already proven that these two are equal, haven't I? Okay, so a minus 2 times 0. All right. Now, solve it for a. So a equals 4. Isn't that fun? Not the worst. Any questions? Number 62. This time we're supposed to discuss the continuity of the composite function h of x equals f of g of x. The simplest thing to do when you can is just make the composite function and then figure out where it's continuous and where it's not. So if h of x is supposed to be f of g of x, and f of x equals 1 over the square root of x, and g of x equals x minus 1, okay? Now, h of x equals f of g of x, right? They tell us that. What's g of x for this problem? X minus 1. So instead of the g of x that I have written there in red, instead of g of x, I put x minus 1. Okay, I've just rewritten this, putting in x minus 1 for g of x. How do I know I can put in x minus 1 for g of x? It tells me. Okay? All right. Now I need to figure out what f of x minus 1 equals. Well, if f of x is 1 over the square root of x, remember how this works? We talked about this the other day. F of, and then whatever's in the parentheses, replaces the x, doesn't it? So that'll be 1 over the square root of x minus 1. If I was finding f of Lucas, it would be 1 over the square root of Lucas, right? I'm finding f of x minus 1, so it's 1 over the square root of x minus 1. Okay, now we can talk about continuity. This is not a rational function because it's got a square root in it, but it's got a denominator. So we need to worry about 0 as our denominator. Since it has the square root in it, we got to worry about negatives under a square root. So we've got two things we need to deal with, right? We need to get a positive number under the square root sign. We can't have negative. We can't have 0. With me? All right. So what guarantees that we get a positive number under the square root sign? X has to be what to guarantee a positive number under that square root sign? Has to be greater than 1, doesn't it? Okay. It can't equal 1 because if it equals 1, that's the square root of 0, which is 0. You can't divide by 0. It can't be less than 1, right? It can't be something like 0 because that'd be a negative under a square root. It can't be a negative number. That'd give you a negative under a square root. So this function will be continuous for all x greater than 1. Understand? Now, I wrote it two ways. You can really just write it one way. But h is discontinuous for x less than or equal to 1, continuous for x greater than 1. And not only is it discontinuous for x less than or equal to 1, it doesn't exist for x less than or equal to 1. And that's how I knew it was a non-removable discontinuity. The function doesn't even exist for x less than or equal to 1. Still hanging in there? Number 70. Describe the intervals on which the function is continuous. Now, they're giving us too much information here. Not in like the gross ew way, but just more stuff than we need to know. If I've got the graph, I don't need to know the definition of the function. Okay? So where's this function continuous? Is it continuous to the left of -3? No, it doesn't exist. Is it continuous to the right of -3 forever? Yes. Now you notice this book does not put arrows. That's okay. If they intend for it to end, they'll put a dot. So it goes on forever. So this function is continuous as long as x is greater than or equal to -3, isn't it? And then there's a bunch of different ways you can write that. You can write what I wrote. F is continuous on the closed interval from -3 to open at infinity. You could have simply said continuous for x greater than or equal to -3. Either way. In fact, be able to do both. You don't have to do both. Be able to do both, because who knows what's going to be the favored method of your teacher next year. And I know that the AP test uses both methods. So you've got to be familiar with both. Does that take care of 70? All right, well, that wasn't so bad. 76. Trombones. That's just hard to not think that when I see 76. All right. In exercises 75 through 78, explain why the function has a 0 in the given interval. Remember the intermediate value theorem? That's because you were in the bathroom. Everybody else, remember the intermediate value theorem? It occurred to you about 20 minutes ago. All right, so f of x equals x cubed plus 3x minus 2 on the closed interval from 0 to 1. All right, to apply the intermediate value theorem, we have to have the function continuous on the entire closed interval. Now look at this function. It's a polynomial function. We have a theorem that says polynomial functions are continuous throughout their domain. What's the domain of a polynomial function? It's all real numbers, right? So if this function is continuous for all real numbers, it's got to be continuous on the closed interval from 0 to 1. So I state that because I'm getting ready to use the intermediate value theorem. I got to show that I can, okay? So f is continuous on the closed interval from 0 to 1. Then we need to know what f of a and f of b equal. Because if I'm going to show that there's a 0 between 0 and 1, hadn't f of a and f of b better have one of them positive, one of them negative? So let's see what they are. So f of 0 equals -2. How did I get that? I went to f of x, I put in a 0 for x, and I get -2. And f of 1 equals 2. How did I get that? I went to f of x, I substituted in a 1, and I got 2. So that's good. F of A is negative, F of B is positive. The intermediate value theorem guarantees that for every number, let me rephrase this so it's more clear, that for every y coordinate between -2 and 2, there's at least one place it's on the graph. Okay? That's what the intermediate value theorem guarantees, that for every y coordinate between -2 and 2, there's at least one place that y coordinate's on the graph. I found f of 0. Put 0 there and there. Now, so in other words, the intermediate value theorem guarantees there's at least one place where the function value equals 0 on this interval. So that's what we need to say. By the intermediate value theorem, f of c equals 0 for at least one c, for at least one x coordinate in the closed interval from 0 to 1. The intermediate value theorem is kind of a big deal. Okay? Let's do 79. Use the intermediate value theorem in a graphing utility to approximate the 0 of the function in the interval from 0 to 1. Repeatedly zoom in on the graph of the function to approximate the 0 accurate to 2 decimal places. Use the 0 or root feature of the graphing utility to approximate the 0 accurate to 4 decimal places. All right. Before I do that, I need to be sure that the intermediate value theorem was going to apply. So what has to be true for the intermediate value theorem to apply? Has to be continuous on the closed interval from 0 to 1. And then if I'm going to find zeros, the y-coordinate at one endpoint's got to be negative, and the y-coordinate at the other endpoint's got to be positive. So let's see if they are. Figure out what f of 0 equals. What's f of 1 equal? So f of 0 equals -1, and f of 1 equals 1. Does this prove that there's got to be at least one 0 of this function on that interval? It does. So we say so. The intermediate value theorem guarantees at least one 0 on the interval. All right, now, the way they want us to find it, let's use our calculator. Y equals x cubed plus x minus 1. We'll graph that. Now our interval is from 0 to 1. So I'm not even sure I know how to use zoom in. I'll see if I do. Zoom in. I don't know, hit enter. Okay. Should I trace over closer to the 0? Oh, I need to do this. Where's my cursor? Does anybody see it? Oh, there it is. So if I get that close and I zoom in now, does that zoom in on that little dot? Okay, so I'm getting closer. I can trace over. Oh, how'd I leave the graph? There we go, because I didn't hit trace. So there's where I'm crossing. So rounding 0.69, 0.68 probably. All right. I don't like that. I'd rather do this. Let's see if I remember what it is. Second calc and choose 0. Okay? Some of yours may say root. I don't know. But for me, it's 0, which is number 2. And then it wants you to give a boundary. The reason they want a boundary is because many graphs cross the x-axis more than once. And the calculator wants to know which one you're looking for. So give it a boundary. Make sure that your left boundary is to the left of where the graph crosses. Hit enter. Then move over and make sure that your other end is on the right side of where the graph crosses. It wants you to make a guess, again, because many functions have more than one 0, but we've only got the one, so that's a good enough guess. And there we go, 0.6823. Now, on the AP test, they always have you list answers to 3 decimal points. And they don't even care if you round it or truncate it, which means you just write down the first 3 digits and leave off the rest. They take it either way, which kind of amazes me they don't make you round it. But they don't. So if I write down 0.682, I'm done as far as the AP people are concerned. Okay? So try to get in the habit, even if the directions say 4 decimal places, okay, give them 4. All right, give them the 4. But realize on the AP test, all you can do when you go past 3 digits is mess it up. Okay? If I accidentally wrote down 7 instead of 3, they may say, whoa, idiot. All right? So just for the AP people, just give them what they want, which is 3 places. All right, we good? And by the way, using the 0 function on your calculator is something the AP test expects you to be able to do. So forget the zoom in stuff. Be able to use that 0 capability on your calculator. They expect you to be able to do it. And since they expect you to be able to do it, that means that most colleges are going to expect you to be able to do it. I mean, that's where they get their expectations. Colleges tell them. Okay? All right. 86. Verify that the intermediate value theorem applies to the indicated interval and find the value of C guaranteed by the theorem. All right, so we've been practicing making sure that the intermediate value theorem applies. We've got to have a function that's continuous on the entire closed interval, and then since we're not having to find zeros here, we'll just need to figure out what f of A and f of B equal. Okay? So f of x equals x squared plus x over x minus 1. The closed interval is 5 halves 4, and f of c equals 6. All right. So that's what we have to guarantee, is that happens. Okay? That it crosses 6. So one of our endpoints will have a y value less than 6. The other one had better have a y value greater than 6, hadn't it? Okay? All right. Is this a continuous function on that interval? Let me ask it this way. If I don't know an interval, where's the only place this function is not continuous? 1. Is 1 in this interval? So our function is continuous on that entire interval. We got to say so. F is continuous on the interval, closed interval from 5 halves to 4, and explain why, because x equals 1 is not in the interval. Now, find f of A and f of B, and I just use my calculator to do it. F of 2.5 turns out to be 5.833. f of 4 turns out to be 6.667. Trust me. So, does it seem like there ought to be at least one y-coordinate of 6 between those two endpoints? Yeah, there better be. Okay, the intermediate value theorem states that f will have every value from 5.833 to 6.667 when x is in that interval. Better yet, there exists a C, the intermediate value theorem says there exists a C, and I could have even said a C in the interval between 5/2 and 4. I probably should have. I probably should have said a C in the interval from 5/2 to 4, such that f of C equals 6. All right, so all of that was for what I just underlined in blue. Now, find that value of C. So in other words, find the x-coordinate or coordinates that make this function equal 6. I don't know how accurate an answer you'll get graphing it. How about just setting the function equal to 6? So to find the x-coordinates for which the function value equals 6, set the function equal to 6. Everybody with me? All right, how about we start off by multiplying both sides by x minus 1. That'll give us x squared plus x on the left. When I distribute the 6, that'll give me 6x minus 6 on the right. So we have a good old-fashioned quadratic equation. Subtract 6x from both sides, add 6 to both sides, and we have it in standard form. Is this one factorable? What are the factors? So, the factor x minus 2 times the factor x minus 3 equals 0. So what are the roots? What are the zeros? What are the x's? 2 and 3. Now, remember what we're doing. We're finding the C. We're finding the x-coordinate that's between 2.5 and 4 that makes the theorem true. So which one's between 2.5 and 4? 3. All right, so the answer should look something like that. Ooh. Do the rest of this, however much you haven't done. Anything that was giving you trouble yesterday, hopefully you have a better shot at understanding it now, even if we didn't go to specific questions. We talked about more of the same stuff. And that's going to be the next assignment. So if tonight's a good night for you to do some work, then you just keep on rolling.